In dense urban NRV2X, blockages kill uplink reliability. Multi-hop relaying restores coverage, but relay selection is an NP-hard optimization problem. Traditional mixed-integer linear programming is accurate but computationally prohibitive for real-time decisions. Researchers from FUB and Uni-Roma 2 propose a solution: a Graph Isomorphism Network with edge features, or GINE, for low-latency relay selection. The system models the V2X environment as a directed graph. Nodes represent connected vehicles and roadside units. Edges denote feasible wireless links. Crucially, the GINE integrates edge-level radio, attributes directly into the message-passing mechanism. Each edge feature encodes achievable capacity, derived from instantaneous SNR. The update rule concatenates incident node embeddings with a learned projection of the edge features, allowing the network to jointly reason over topology and link quality. This is a learning to optimize framework. An offline MILP oracle generates ground truth relay configurations, supervising the GINE via class-weighted binary cross-entropy loss. The model learns to infer binary edge activations that maximize connectivity. On a large-scale dataset generated via an OSM Sumo GEMV2 pipeline simulating Rome, the GINE achieves 95.9% accuracy and an F1 score of 0.954 against the MILP oracle. Inference latency remains strictly bounded under 5 milliseconds, scaling linearly with edge count. Furthermore, the authors introduce a hybrid strategy, GP-MILP. The GINE prunes the MILP search space at a recall-oriented operating point. This reduces solver runtime to under 30 milliseconds for 98% of instances, while preserving MILP-equivalent objective values. The result is up to 12% connectivity gain over single-hop baselines, demonstrating that edge-aware graph learning enables MILP-grade optimality within stringent NRV2X latency budgets.